Okay, finally today we're going to wrap up 4.4 on day 5 of it. So today we're going to look at particle motion with integrals. We already looked at particle motion earlier with derivatives, so today we're now going to look at it with integrals. I have these 3 integrals outlined to the left, and I want to go through piece by piece with them and explain to you why I'm saying the things underneath them. So for instance, I'm saying if I integrate velocity function from a to b, it's the net change in position from a to b. This is also known as displacement, and then here you can see why it's the net change in position. So off to the side, let's look at this. If you integrate velocity from a to b, what function do you get? Do you remember if you took the derivative of position, you get velocity? So if we took the derivative of position, we get velocity. Now we're going backwards. So if I integrate velocity, I'm going to get position. And because it's a definite integral, it goes from a to b. Then we can say x of b minus x of a, and that's how we get all this stuff on the left. So if you just think about what you're doing about integrating velocity to get position, it's the net change in position. Okay, again, let me go back up to the top and restate all of this in terms of derivatives. So I already told you over here, if you take the derivative of position, you get velocity. Now, do you remember if you take the second derivative of position, what do you get? So what I'm doing is I'm taking the derivative of x prime to get x double prime. The derivative of velocity is v prime. And what does that give you? Acceleration. So now if I'm going backwards and if I integrate acceleration, I'm going to get velocity. If I integrate velocity, I'm going to get position. So on this next one, when I'm asking what do we get when we integrate acceleration? Well, we know it's the velocity function from a to b, which is the velocity at b minus the velocity at a, which up above, this was the net change in position. Now we have the net change in velocity. You want to make sure when you're writing these sentences out, if they ask you to describe what you're doing, that you're going to say it's the net change in velocity from A to B. Okay, going on. What is 3? This is going to be the total distance traveled. So look at the difference between these. This right here has absolute value on velocity, and if you look up above, this one does not. So the absolute value, the reason it's going to give you total distance, let's go over to the right here and let's sketch this function. Let's draw a parabola that does this. Okay, and let's call this B and this A. So if I integrate just the velocity curve, I'm going to get this region, and this region. And it's going to give me the net change in position, which we saw up above in 1. But if I integrate the absolute value of velocity, what it's going to do is take whatever is below the x-axis and flip it up, right? That's what absolute value does. So it's going to take this piece and flip it up. So I'm going to get this, and instead of going down, it's going to flip up and then continue on. So do you see this piece? All I did was flip it up this way. So now do you guys see that this is all positive now? And again, if this goes from A to B. So the net change, what it's going to do is anything below the x-axis, it's going to assign a negative value. But once we put the absolute value, anything above is going to give me the positive, which is going to give me total distance traveled. So like in this case, this would be a positive and then a negative and then another positive. So this piece is going to negate some of this, where this all counts as positive and I get total distance traveled. So like if I went from here to here, and then back to here, right? Total distance traveled, we would want to add all these things up. Whereas net change would just change take the difference between where you started and where you ended. Okay, so motion summary. Again, if they ask you for displacement, it just means the net change in position and you just integrate the velocity function. But if they want total distance traveled, you have to make sure you put absolute value so that you count that negative piece, which means going backwards or down, as distance. And then if you want the position at a certain value, what you're going to do is take the net change in position, so how much it changed by, and add on to where you started. Okay, so I want you to get the difference between all of these, and then look at what it said down below to make sure you include units in your description. Again, this is the net change in position. And then the beginning part is the position at t equals a. Okay, going on to example 1. Okay, reading through this, it says the velocity moving on a horizontal axis is given by this equation. Okay, so we're dealing with velocity. We have a restricted domain here, and they tell us the starting point on the horizontal axis for the particle is 1. That means the starting point, and since the time goes from 0 to 3, the starting position is 1. Okay, we're going to read the question, and the hardest part here is just the setup. So when we read find the displacement, what does that mean? Well, displacement means net change in position. So we're looking for x of 3 minus x of 0. We don't care what happened in between. We just want to know the difference between where we started and where we ended. So to set the net change in position or displacement, we are going to integrate the velocity function. If we integrate that, we're going to get 4t minus t cubed over 3 from 0 to 3. Sub a 3 in, you're going to get 12 minus 9 minus 0, so 3. So we have our net change in position is 3. We use units. Position in this case is measured in centimeters. Okay, now the next one doesn't ask for displacement. It's saying find out exactly where we are after 3 seconds. So to find out exactly where we are, that means position at 3. Well, what we need to do is write down, this is like the notes from yesterday, we have to write down the position where we were in the beginning plus the net change in position, how much we changed by, which is going from 0 to 3 of 4 minus t squared dt. Now x of 0, they told us back in the beginning, x of 0 is 1, so you're going to go ahead and write a 1 down with the pen. And then I'm going to speed things up a little here. Do you guys see 0 to 3 of 4 minus t squared? Didn't we just do that and find out it's 3? So we already did that above. So let's just say 1 plus 3 and we get 4. Okay, we don't have to do anything more than this. If you remember what I did yesterday, I made a table to link these two questions together. Look at if you have time and position. At time 0, you're at 1. They told us that up here. We just found out that at time 3, and actually let me fix this, and let's write x of 3. At time 3, you're at 4 centimeters. So at time 3, you're at 4. What was the net change? Look up above. Wasn't the net change 3? So if I started at 1 and it changed by 3, it would make sense that I end up at 4. Okay, because 3 is the net change. Okay, C, this says calculator. So go ahead and grab your calculator out. This is to find the total distance traveled for the time interval between 0 and 3. Total distance traveled, what happens is if we go forwards and backwards, right? Well, let me write it a little differently. If we go forwards this way and then backwards this way, right? Total distance traveled, we want to add up this length plus this length. So we want to count the negative part going back, so we need to make it positive. So in order to do that, we're going to use absolute value. Because they said calculator, let's just set it up. We're going to integrate the absolute value of the velocity function from 0 to 3. Now, because we're using our calculator, I didn't want to write out 4 minus t squared. It was easier just to write v. So let's go to our calculator now. Because we're not using this function more than once, we're not going to type it into y1 because we don't need to keep using it. So let's just hit math 9, and then we're going to integrate from 0 to 3. And what function are we going to integrate? The absolute value. Remember, we hit math, we go over to number and hit enter, and it's going to be 4 minus t squared, so 4 minus x squared, and then dx. And our answer is 7.667. Okay, so let's go back to our notes and write that down. Remember, for the calculator, I need you to write down the integral, which you did, and then the answer. And then let's put units on this. So 7.667 centimeters is the total distance traveled. Do you guys see that the total distance traveled, which is 7.667, is not the same as the net change? Okay, because you're going forward and backward. So the net change, you only changed your position by 3, but we actually traveled a lot more. That would be sufficient for this problem. I also want to show you how to do this if you didn't have a calculator. Okay, let's go ahead and graph this. We're graphing the position function. So 4 minus t squared, that's going to hit at, when t is 0, the velocity is 4. It's also going to hit at 2 and negative 2. We're only going from 0 to 3. And then at 3, it looks like, what will the value be? Negative 5? Okay, so I'm going to do my best to sketch this. Okay, so the total distance traveled. We actually want absolute value, but do you see that some of this, if I'm going from 0 to 3, is below? So what we really want to do is take this piece below and flip it up. To do that, we're going to have to negate it. So I'm going to, because this is going to give us a negative value, right? So when we go to do this, we're going to have to put a negative in front of it. So we're going to want to integrate from 0 to 2 just fine, 4 minus t squared dt. But then we're going to put a negative in front of the piece from 2 to 3 of 4 minus t squared dt. This negative here, remember, it's because we're going to take this piece and flip it up. So we need to make it positive. Okay, integrating this quickly, 4t minus t cubed over 3 from 0 to 2 minus, now we have a subtraction here, 4t minus t cubed over 3 from 2 to 3. If we sub a 2 into the first part, we're going to get 8 minus 8/3. If I sub a 3 in here, I'm going to get 12 minus, what is that? 27 divided by 3 is 9. Minus, if I sub a 2 in, it's 8 minus 8/3. Okay, going on, we're going to have 8 minus 8/3 minus 3. Now right here, instead of combining, so I have 8 minus 8/3. This is 3, so minus 3. Then do you see that this negative takes out that negative? So then I'm going to have plus 8 minus 8/3. I was trying to leave my fractions for the end. So then going on, I'm going to get 8 plus 8 is 16. 16 minus 3 is 13. So 13 minus 16/3. To get common denominator, 39/3 minus 16/3, which is 23/3. What is 23/3 about? It's approximately 7 2/3 centimeters, which is exactly what we got a long time ago using our calculator. Okay, so again, on this problem, if we had calculator, this would have been the way to go. If not, you have to find the x-intercept to find the pieces that is below, and then you need to integrate by putting a negative in front of it to flip it up. Okay, average velocity. Now there's two ways to find average velocity. One way is to take change in position over change in time, and the other way is just to go ahead and integrate velocity. So you have to see what you have. On this problem, they gave you velocity. So we can go ahead and do that. We're just going to do 1 over, this is the average value formula. So 3 minus 0, 1 over b minus a. Then we're going to integrate from 0 to 3 of v of t dt. I'm writing v of t on purpose here so that I can show you that average velocity means to integrate velocity, so long as you divide by b minus a. So then I'm going to have 1/3. When we integrate actually from 0 to 3 of 4 minus t squared dt, didn't we do that up above? Look at 4 minus t squared dt from 0 to 3 is a 3. So when I go to write this out, we can just say that this is going to be 1/3 times 3, which is 1. What unit should go on this? We should have 1 centimeter per second. Because this question asked us so many other questions, we have other data that we could have used. To get average velocity, if you have the velocity function, this would be the way to go. Do you guys remember the other way to do it? It was x of 3 minus x of 0 over 3 minus 0. X of 3, if you look up above at the table, x of 3 is 4 and x of 0 is 1. So it's going to be 4 minus 1 over 3. 3 over 3 is 1, which is exactly what I got right there. Okay, so because we had position data as well as velocity, we could have done it either way. Okay, average acceleration. We don't have the acceleration function to integrate, so we cannot use this. But what we can do is use the other formula. It's v of 3 minus v of 0 over 3 minus 0. We have the velocity function, so over here, let's find v of 3. V of 3 is found by subbing a 3 in, which is -5. V of 3, or we already found v of 3. V of 0 is 4 minus 0, which is 4. That's going to give us -9 over 3, which is -3. So the final answer is going to be -3 centimeters per second squared. Okay, under 15 minutes, I think, and we're done with particle motion. See you guys.